This is video number 2 in our lesson on the synthesis of substituted arenes. In this video, we will focus on oxidation of the benzylic position of alkyl benzenes to make benzoic acids. As we get started, I would like for you to make a prediction. Which of these compounds, benzene or toluene, do you believe is more carcinogenic or equally carcinogenic? Or no idea? Write down a prediction. And we'll come back to that. As promised, let's discuss oxidation of the benzylic position. Treatment of alkyl benzenes with potassium permanganate under aqueous basic conditions can lead to the complete oxidation of the benzylic position to form benzoic acids. Someone may have worked hard to install this alkyl group here via Friedel-Crafts alkylation. However, when treated with this strong oxidant, potassium permanganate is a strong oxidant. The benzylic carbon is completely oxidized. This carbon-carbon bond breaks, this carbon-hydrogen bond breaks, this carbon-carbon bond breaks. And those bonds are replaced with 3 bonds to oxygen, and this carboxylic acid group results following an acidic workup. This very interesting reaction will occur for any alkyl benzene with at least one benzylic CH. In fact, if this alkyl benzene with this nice long alkyl chain was treated with potassium permanganate followed by an acidic workup, benzoic acid would result. Following cleavage of all of these bonds and complete oxidation of the benzylic carbon. You may have noticed I wrote benzoic acids, not benzoic acid. And although this particular reaction did make benzoic acid itself, different substituted benzenes will make substituted benzoic acids. For example, please predict the product of the reaction of this dialkyl benzene under the same reaction conditions. Treatment with potassium permanganate under basic aqueous conditions, followed by acidic workup. Identifying the benzylic positions of the 2 alkyl groups for this dialkyl benzene. We notice that one of them has benzylic hydrogens and the other benzylic carbon does not have any CH bonds. Thus, this carbon with no benzylic CH bonds will not be oxidized, but the other benzylic carbon will. The chain will be fully chewed off, resulting in a substituted benzoic acid, where one of the benzylic carbons, the one with the CH groups, was oxidized to the carboxylic acid. The other alkyl group, or the benzylic carbon, did not have any CH bonds, remained intact. I'll just remind you that workup is there to protonate the carboxylate intermediate that results from the oxidation. Under basic conditions, certainly the carboxylic acid would not be formed because it has a pKa of 5. So the carboxylate is the intermediate after step 1, which is protonated with aqueous acid to generate the carboxylic acid. In this example, we see a demonstration that this reaction only occurs for alkyl benzenes with benzylic CHs. Before explaining what that whole benzene, toluene, carcinogen battle was all about, let's try one more example. Let's imagine that this substituted benzene, again, that someone may have worked very hard to make, is treated with potassium permanganate under aqueous basic conditions, followed by an acidic workup. What product do you expect to result from this oxidation? Begin by identifying the benzylic carbons, as we have indicated in pink. Then determine if those benzylic carbons contain at least one CH bond. These 2 benzylic carbons have at least one benzylic CH bond, but this one does not. For the benzylic carbons with CH bonds, replace them with carboxylic acid groups. For this particular alkyl benzene, the product looks like this. where a diacid has been formed. And that's simply because there were two benzylic carbons with at least one CH bond. Now, what does this reaction have to do with anything? This is random. We're chewing off these alkyl groups and replacing them with carboxylic acid groups. That's not necessary. We already know how to make benzoic acid. We don't need to chew up these complicated alkyl groups. We learned a long time ago, even before we started discussing electrophilic, nucleophilic aromatic substitution reactions, that bromobenzene could be treated with magnesium metal in the presence of a dry ether solvent to generate a Grignard reagent, which could be added to solid carbon dioxide, dry ice, and finally subjected with an aqueous workup to generate benzoic acid. So none of this seems necessary. Sure, you could argue that the oxidation of the benzylic position of alkyl benzenes might have some limited synthetic context. However, we will find applications of this method of synthesizing benzoic acid synthetically useful, particularly for substituted alkyl benzenes making substituted benzoic acids. However, an equally important application of this reaction actually happens in the body. Now, not with potassium permanganate, but with the iron-containing enzymes that are located in the liver. As you probably know, the liver processes toxins, particularly nonpolar toxins. We can imagine toluene. Toluene is a nonpolar molecule. It would localize in the liver. And the liver contains oxidants. These oxidants are called cytochrome P450s, and they contain an iron core. And these cytochrome P450s behave very similarly to potassium permanganate, and that they completely oxidize the benzylic position of alkyl benzene toxins that may find their way into the body. So for toluene, benzoic acid would be formed. And for any alkyl benzene with at least one benzylic hydrogen, benzoic acid would be formed. Now, why does the liver do this? What is the point? Well, now the carboxylic acid group, it's polar. Polar molecules will localize in the kidneys where they can be excreted from the body as in urine. So now that toxin, that toluene, it's been oxidized to benzoic acid via similar process, oxidation of the benzylic position. Just in the body, it's with these cytochrome P450s. They have an iron core, heme core with a high oxidation state iron, versus in the lab, we'd use potassium permanganate. Cool, so toluene has been oxidized and eliminated. What would happen though if benzene were ingested? Yes, it is nonpolar, so it would go to the liver, but there's no alkyl group to chew up, no alkyl group, no benzylic position to oxidize. So does nothing happen? Well, those cytochrome P450s are strong oxidants, and benzene gets oxidized, and it makes this epoxide, which is still nonpolar. Okay, so that means it is not going to the kidneys to be eliminated. Kidney eliminates polar substances. So it is still nonpolar, and look at that epoxide. It is really reactive and is going to start reacting with stuff. And by stuff, I mean molecules inside of the body. It can alkylate proteins, it can alkylate DNA. Yikes, that sounds awful, and that can lead to cancer. So the winner of the carcinogen battle is benzene. Benzene is more carcinogenic than toluene, though personally it's a bad idea to ingest either of these compounds. And that's because toluene, being an alkyl benzene, can be oxidized by the cytochrome P450s in the liver to make a polar compound, which is then excreted by the kidneys and urine, whereas that is not the case for benzene, which does not have an alkyl group to be oxidized. So it is oxidized, but it makes this highly reactive epoxide that will, as we said, quote unquote, react with stuff. And if it reacts with DNA, can cause cancer. So there are really two reasons why we learn the oxidation of the benzylic position. One, because we will be able to use it in a synthetic context. And 2, because it's biologically relevant, it represents the laboratory version of a really important process that happens in the body. Pivoting back to the synthetic purposes of this reaction, take a moment and propose 2 synthetic routes to benzoic acid. Each of these routes should start from benzene and then use a different electrophilic aromatic substitution reaction. And if you're feeling really fancy, you can propose 3 distinct synthetic routes. Each one, though, should use a different electrophilic aromatic substitution reaction. Ready, set, go. Perhaps the obvious one would be using a Friedel-Crafts alkylation to generate an alkyl benzene. Just recalling the 6 electrophilic aromatic substitution reactions that we discussed. Now, Friedel-Crafts alkylation requires a stable carbocation, but remember that oxidation of the benzylic position requires a benzylic CH. So we cannot use the most stable cation, which would result from the tertiary chloride, right? That's the prototypical Friedel-Crafts. Well, that would not have this benzylic CH, so we cannot do that, but we could add an isopropyl group and then treat with potassium permanganate under basic aqueous conditions, followed by an acidic workup, and generate benzoic acid. All right, if this carbon-carbon bond in the product is generated by electrophilic aromatic substitution, there's only one more choice for a different, distinct electrophilic aromatic substitution reaction to use in this synthesis problem. We've used the alkylation, time to use the acylation. Now I'm going to keep it simple, but as long as the benzylic carbon has a CH group, it doesn't really matter what acid chloride is used, but I want to waste as few carbons as possible, right? And this carbon is going to become the carbon of benzoic acid, the benzylic carbon. So everything else is going to be chewed up and destroyed by potassium permanganate. So we don't want to add too many carbons on here, that you can have as many as you want. We've seen that already, right? Any alkyl benzene that has benzylic CHs will undergo this reaction. And of course, now that the acyl benzene has been made by the Friedel-Crafts acylation, aka a ketone, to get those CHs on the benzylic position, we will need to reduce using any of the reduction methods that we learned. I will use Clemmensen reduction for fun. So zinc mercury amalgam in the presence of hydrochloric acid. That will reduce that carbonyl to an alkyl group, providing the necessary benzylic hydrogen for the oxidation at that position with potassium permanganate under basic aqueous conditions, followed by an acidic workup. I did say if you wanted to be fancy, you could propose 3 distinct syntheses. Let's be fancy. You might say, well, we've run out of options for making the carbon-carbon bond via electrophilic aromatic substitution. Well, that is correct. But recall, we said, well, we've already made benzoic acid, done it in lab, but from bromobenzene, right? Where the key carbon-carbon bond forming step was made from a Grignard reagent adding to carbon dioxide. Can we somehow use that method and still fulfill the parameters of the question, which is that we must start at benzene and use an electrophilic aromatic substitution reaction? What do you think? Look at our choices up top. Yes, we can. We'll brominate using electrophilic aromatic substitution right here. Okay, so that makes bromobenzene. Treatment with magnesium metal reduces to the Grignard reagent, adds to carbon dioxide in an nucleophile addition step, and protonation generates the carboxylic acid. Good work. Let's try another synthesis problem. Propose a route to the following desired products starting from benzene. And getting started, we should look at the functional groups and we should look at what bonds are made, keeping in mind that benzene is the given starting material for this synthesis. We have identified that these 2 carbon-carbon bonds must be formed to benzene. There are three main ways we have been considering to form carbon-carbon bonds like this. Two of these routes involve electrophilic aromatic substitution to generate the carbon-carbon bond. The third will involve Grignard reaction to generate the carbon-carbon bond, although an electrophilic aromatic substitution will be necessary to generate bromobenzene first, which is then converted into a Grignard reagent. These three different routes make three separate functional groups, although they can all be interconverted, really. Some of those interconversions rely on reactions learned during the carbonyl grid exercise and others during this discussion of aromatic chemistry. Now, in the product, there is an ester, which could be easily generated from any of these functional groups, and an alkene. Because this is a di-substituted benzene, we do need to very carefully consider the relationship between the two substituents in the product. They have a meta relationship, a 1-3 relationship. Now we know that ester is an electron withdrawing group, and so it's a meta director. The alkene, well, I'm not sure what kind of director it is. Yeah, it contains a pi bond adjacent to the ring, so maybe it's a meta director, but I'm not really sure. And also, I know that alkenes are similar to arenes in terms of reactivity, and they're more reactive than arenes. So I probably want to generate this last, or at least after I'm done with the electrophilic aromatic substitution reactions to the ring. And that's fine, since the ester is a meta director, we're pretty sure we will install that group before we install the alkene. But while we're thinking about the alkene, and since we think we're going to generate it last, continuing with our retrosynthesis, let's consider how alkenes are made. Or better question, can alkenes be made from any of these types of functional groups? As we do think that one of these three reactions will be used to generate this carbon-carbon bond in the product. Two reactions come to mind. A Wittig reaction to convert a ketone into an alkene, thinking about this possible synthetic route, ketone to alkene. Or again, using the ketone, there could be a Grignard and elimination sequence. Both of these routes could install an alkene from a ketone, which could easily be obtained from a Friedel-Crafts acylation. The only issue, and the issue is with this second option, which does go via this alcohol. The E1 elimination step 3 here, would eliminate water and generate the alkene. Right, so it generates the alkene here, right, like right here. Okay, now the only problem with this sequence is that Grignard reagents would also react with the ester. So if you imagined that your retrosynthetic analysis proposes this intermediate, recalling again that the ester was installed first because it is a meta director and would direct the second acylation here. Also, because the alkene is reactive with pretty much everything, more so than a benzene ring. So we want to put that alkene on last. All right, step 1, adding the Grignard. It would add to the ketone as we desire, but Grignards also react with esters, and that just cannot be controlled. So we don't know any way to protect the ester, so that really rules out this Grignard route number 2, because this would react with the ester. Okay, good idea, but it will not work. That's okay, because that just leaves us with one possibility for how to install the alkene. We'll need to use the Wittig. And because we're swapping oxygen with CH2, that's the desired reaction, then we just use this methylene Wittig reagent. And if you're asking, oh, why doesn't the Wittig reagent react with the ester? They don't. Wittig reagents are mild enough that they do not react with the less electrophilic ester. We have the last step worked out now. Good job, yay for retrosynthetic analysis. Now we need to generate this intermediate from benzene. I think we can do it. We've decided to install the ester first and then the ketone. That means thinking backwards that this intermediate, this molecule with the ester and the ketone, will be generated from the ester, making this carbon-carbon bond in a Friedel-Crafts acylation. Now thinking about how to generate the ester functional group, we can't do so directly. We will need to use one of these three reactions and then convert the product into the ester. We have some options for doing that. Perhaps we want to try the ketone because it seems pretty easy and we remember the Baeyer-Villiger reaction. So we think, all right, can we do the Baeyer-Villiger reaction using MCPBA to oxidize the ketone to the ester and inserting oxygen here. Now we could just generate this ketone via Friedel-Crafts acylation. Pretty straightforward. We'll be good to go, right, with this ketone from here. Well, the only problem is thinking about the Baeyer-Villiger. It's phenyl versus a primary carbon. Phenyl migrates faster, so the desired ester will not be formed. In fact, a constitutional isomer will be formed and is undesired. So Baeyer-Villiger was a good idea, but it will not work for this to generate the desired ester. That's fine. That means we can't use Friedel-Crafts acylation to put in that ester, and that's okay. We have two more options. We have the alkyl benzene and the carboxylic acid. Let's first try Friedel-Crafts alkylation to generate the ester. Now, the idea behind this, behind generating the alkyl benzene, is that we know this side chain can be oxidized off to form a carboxylic acid. Using the reaction that we just learned, treatment with potassium permanganate under aqueous basic conditions followed by an acidic workup. We know how to convert acids to esters from our work with the carbonyl grid and acyl transfer reactions. Since there is an ethoxy group desired on the ester, ethanol should be used in the presence of an acid catalyst. All right, excellent work. So that works, right? Well, we didn't put in our reagents for the Friedel-Crafts alkylation, but we can do that. So there's aluminum chloride and then the isopropyl chloride to generate the isopropyl benzene. We do need this allylic hydrogen for the benzylic oxidation to work. Then an esterification of an acid generates the ester. Another Friedel-Crafts acylation generates the ketone, and a Wittig reaction generates the final product. So the ester can be made from the alkyl benzene. We said it cannot be made from the ketone because the Baeyer-Villiger will not work. However, let's try this Grignard root as well because notice something here. The Grignard root generates a carboxylic acid, which is an intermediate that we're using. So we can also generate that carboxylic acid using the Grignard method, so via bromobenzene. Let's try that now. So I'll indicate it in purple. Since it's just you don't have to put both answers if you were answering this question on an exam. This is just to show you all the different possibilities, and especially in case you came up with them on your own. Now, electrophilic aromatic substitution generates bromobenzene, and then as we have already outlined, treatment with magnesium metal under dry organic solvent conditions makes the Grignard. When dry ice is added, the Grignard reagent as is a nucleophile to CO2, and then an acidic workup is necessary to generate the final same carboxylic acid intermediate here. Follow the same pathway to make the product. You might want to listen to this problem a couple of times, make sure that you understand this is a complex problem, but we're working up to this level of problem solving now, and you really can do it. Excellent. When you're ready, let's summarize benzylic oxidation. That's the key reaction learned in this section of our lesson on synthesis involving aromatic compounds. Perhaps try this on your own and then compare with my summary. We learned that any alkyl benzene with at least one benzylic CH will undergo full oxidation at the benzylic position, the carbon adjacent to the phenyl ring. to yield a carboxylic acid. If this was simply a monosubstituted benzene, just an alkyl benzene, then specifically it yields benzoic acid. However, this reaction works as well for substituted alkyl benzenes to yield substituted benzoic acid. So there can be other substituents there as long as they're compatible with these conditions. And then, of course, we saw if there were two alkyl groups, let's imagine we have this molecule, dimethylbenzene, orthodimethylbenzene, which has a common name I will spare you from. Both of those benzylic positions would be oxidized under these conditions to yield a diacid because each of those alkyl groups, each of those methyl groups, has at least one benzylic CH. Why did we learn this reaction? Well, it's kind of useful in synthesis. It can be useful in synthesis. We've just worked out a few problems where we could utilize benzylic oxidation as a key step. We also found some alternatives to it, right? But it is honestly more interesting because it is the laboratory version of the processing of aromatic compounds that occurs in the liver. And you can recall that explanation from this slide. Well, this does conclude our discussion of the oxidation of the benzylic position to make benzoic acids. Once you're ready, move on to the next set of reactions, which I will explain in another video.